Can you hear me? Okay. Well, first, thanks a lot to the organizers. Yeah.
I was going to introduce you, but like.
Okay. Yeah, I'm Sebastian Hurtado. I was a master student here. You know, yeah, like 15 years ago, and yeah, it's excellent to be here. And thanks to the organizers for organizing this excellent conference here in Rio. And okay, so I'll tell you a little bit about the things I've been thinking about. And so it's like what I'm going to say is related to one of the lightning talks yesterday. And so I'm going to start with like an elementary question. Is my voice clear over there, or is it too loud? Good, we're good? Okay. So, there's like this elementary question that it seems to be open, okay? I mean, I couldn't find, so suppose you have some subgroup between SL2Z and SL2C square root of 2, or maybe if you don't like square roots, okay, then you can ask like a similar question for SL3, for subgroups of SL3Z. So for example, you can ask, so I haven't asked the question yet, okay, the question, so suppose you have a subgroup that, I mean, of SL3Z that contains this subgroup, okay? And then, so the question is, so you have this subgroup, and then is like gamma either SL2C up to finite index, or is gamma SL2C finite, or like SL2C square root of 2 finite. So for example, you could like just ask, like just take a couple of matrices, like okay, the generators of SL2C, and then add another matrix, and like, well, okay, I got one already for you, and you can ask if this subgroup here, if it's a finite index subgroup of SL2C square root of 2, okay? And this problem can be like approached computationally. You could like, you know, take a computer program and write a computer program and check whether this specific group or you know, like maybe one project, it could be just like, you know, like take, how large can you take this matrix and see like if like a computer program tells you like whether this is a finite index subgroup or not. Okay? Is the question clear? Okay, and the yeah, so let me, okay, you know that SL2C is a lattice in SL2R. It's a lattice in SL2R, but SL2C square root of 2, well, this might not be known for everybody, that it's a lattice in SL2R times SL2R. So you can embed this subgroup here into SL2R times SL2R just by sending matrix into just like the matrix and here like the Galois conjugate. So that means you, for every entry is A plus B square root of 2, then you change to A minus B square root of 2. And so I mean, if you forget just about the SL, it's just C square root of 2 is discrete in R times are in this way, and it's a lattice in R squared, and the same thing happens for SL2C square root of 2, but of course this is not trivial. And yeah, so this question, okay, and what is the good thing of this is that, okay, now this becomes here in this embedding, it becomes a discrete subgroup, and like this question then can be phrased into this more general question that I'll state is, so suppose, so the general question would be, let's say G is a simple or semi-simple Lie group, and so suppose you have gamma, a subgroup, discrete subgroup, and gamma 0 a lattice in G, and let's identify gamma 0 with, I mean, you have like a diagonal embedding. I gamma 0 is like, or I is the diagonal embedding, or maybe delta, the diagonal embedding of G times G, or G into G times G. And suppose gamma 0 is a lattice, and suppose gamma is discrete. Zariski dense, well, Zariski dense just means it doesn't lie in a smaller subgroup of G, Lie subgroup. And the second condition is that gamma 0, or this diagonal embedding, is contained in gamma. And then the question is, does this imply that gamma is a lattice in G? Okay. Are there any questions? G times Z, right? G times Z. Gamma is a subgroup of G times Z. Yeah, sorry. Yeah, gamma is a subgroup of G times Z. Okay. Yeah, so why am I interested in this question? Okay, so let me tell you, okay, a little bit of like, okay, related work to this. So a bit of like history related to this problem. Yeah, but maybe like the motivation. So like the motivation is like understanding discrete subgroups of SL2R times SL2R. Like, okay, the discrete subgroups or finally generated subgroups of SL2C is like the theory of Kleinian groups, and it took like 100 years, more than 100 years to understand. And but like when it comes to SL2R times SL2R or like SL3R, it seems like we don't have many examples of like infinitely, or there are like these Kleinian groups that are called quasi-convex. No, what's the name? Geometrically finite. But in SL2R times SL2R or SL3R, there are not many known subgroups apart from kind of like, for example, perturbations of these subgroups, which are called like the Anosov subgroups, or things related to this, and lattices, and it seems like, okay, it is very difficult to construct them. So, yeah, so for example, there's like a question of Serre, like from 1970s, whether every like subgroup of SL3Z is coherent like using the notation from yesterday, that whether every finally generated subgroup of SL3Z is finally presented. And what else? There's a question of Alan Reed that asks whether a hyperbolic three-manifold group embeds into discretely in SL3R. Okay, this is related to the lightning talk yesterday, where as a hyperbolic three-manifold group embeds in SL2R times SL2R. Okay, what else should I say? Yeah, so I'll say a little bit. If you were going to prove like this group is a lattice or not, there are not many kind of like tools available. I'll mention some just because I think that they're important, like historically. So there is like a result of like Selberg, and okay, I'll also put like Hiob because that was part of her thesis, and Yves Benoit, where, I mean, it says that if you manage like somehow to show that with these matrices you can generate something like this matrix, okay? So if you manage to show that your subgroup contains a Z2 unipotent, like, then this group is a finite index subgroup, okay? So that's kind of like some positive evidence. Yeah, this was in the okay, at least this one was in the early 90s, and there is some recent work of Fracik Gelander that apply for simple Lie groups, and that says that if you have a discrete subgroup with bound on the injectivity radius of the locally symmetric space associated to it, like you take the space quotient by gamma, and this thing has an upper bound on the injectivity radius, then this is actually a lattice, okay? But the problem with like this result is that, okay, this is kind of difficult to check whether something has bounded injectivity. I mean, if I ask you, okay, does this group has bounded injectivity radius in SL2R times SL2R? Okay, it's kind of difficult to really test. Okay, so what else? Yeah, and also, okay, I should put this because this was like a related work that this was in the simple case, and in the semi-simple case, like products of SL2R, this was very recent, like this 2024. Bader, Gelander, Levitt. I think I might forgot someone here, but I hope it didn't happen. Okay. Yeah. So. Yeah. So there's kind of like also like a question of Nori, Madhav Nori in 1983, which asks, so suppose you have a discrete subgroup of a simple Lie group G, and you have some H containing in G and H of higher rank. So you should think maybe this G is SLNR, and this H is here SL3R, okay? And you know that gamma intersection H contains a lattice, contains a lattice in H. In H. And then the question is, does it imply okay, maybe you have to put a little bit more conditions on this, and I think that's the question of Nori, but does it imply that gamma itself is a lattice? A lattice. Okay, and yeah, gamma Zariski dense. Yeah, gamma Zariski dense. Yeah, thanks for the all corrections. Yeah, it will happen again. You will have to correct me again. Okay, I promise. Yeah. Okay, I'll try to be there more than 5 minutes. We'll see. Okay. Yeah. So that's like the question of Nori. Are there any questions about like the definitions or anything? Okay, so yeah, so I'll tell you like some of our results. So our results are okay. Forget it. I didn't say anything. Okay, so then let me start. Theorem 1. So theorem 1 says the following. It says within this settings, exactly in the setting of this question here, and so it says assume the conditions here. So you have exactly these conditions. Here discrete output. Okay. Then, well, one, like this gamma is not, it's not a free product. Okay, so it's not, you cannot just kind of throw like a random matrix, okay, and expect this to be discrete and free, okay, and a free product. So it's, yeah, so it's kind of like, somehow it tells you that you cannot play ping pong if you play ping pong like in the standard way, okay? And so gamma is not isomorphic to this thing. And the second result, it tells you that somehow if gamma 0 was like a lattice that has algebraic entries, so for example, this always happens if the Lie group is different from SL to R, and then gamma itself has to have algebraic entries. So let me write this. So more precisely, this says that if gamma 0 has algebraic traces, and so what do I mean by algebraic traces? I mean that, okay, I'll say it in a bit, but then gamma has algebraic traces. And the other thing is that if the traces are not only algebraic integers, but are like actual, algebraic numbers, but actually algebraic integers. So if gamma 0 has integral traces, then gamma has integral traces. Okay? and let's say the definition of algebraic traces. So that means just, okay, you have like you have these two projections from G times G into G, and let's assume this is a linear group, so it lies in some SLN. And so what I mean by that then is like, so gamma has algebraic traces or integral traces if, like, for every gamma and gamma, the trace of pi of gamma, pi I of gamma, for all I 1 and 2, these are algebraic numbers or integers. We are like, okay, so like this number is an algebraic number, but it's not an algebraic integer. It doesn't satisfy like the minimal polynomial. It has a coefficient. The top coefficient it has a number that is not 1. Okay, so yeah, this one is not integer. Okay. Are there any questions about the statement? Yeah.
You are assuming that delta of gamma is equals containing gamma.
Delta, yes, I'm assuming here this. Also Zariski dance. Am I assuming also Zariski dance? Yeah, right. Even though it's still true, right? Okay, okay. No, yeah, I'll assume it's Zariski dance. Yeah. Yeah. Mm-hmm. Any other questions? Okay, so yeah, so let me tell you. Okay, before I tell you something about the proof, well, I'll tell you that first, like when we proved this, like part first, we had like a different proof than the one that I'm gonna like give today. But like later, we kind of found out that like there's like this work of Venkataramana Chatterjee. So there's like important work of Venkataramana Chatterjee, and like the ideas there kind of like give a much nicer proof of our result, and also it's an unpublished paper of 2009, and well, that I thought for many years that it was incorrect. Okay, I mean, just like I don't know, I had like, you know, and talking to people, but now like, okay, I believe it's correct because otherwise, yeah, I can't prove this thing. But like, I mean, I have checked things till the point that I feel comfortable saying, okay, I have a proof, and yeah, or we have a proof, but yeah, Venkataramana Chatterjee, there's like this paper, and they even prove something kind of more impressive. That is, like, suppose like the G has higher rank, okay? So it wouldn't work in the SL2R times SL2R, but assuming this condition, what they prove is that this group is super rigid, okay? So like as in, I don't know if you know Margulis superrigidity, that says that any kind of linear representation of this group extends to the Lie group, of the discrete subgroup extends to the Lie group. And they proved that this group is like super rigid. Okay, so whatever it is not. If it's not a lattice, it's a very weird stuff. Okay, and what else should I say? Yeah, I mean, but the ideas here are also based on the ideas of the proof of Margulies' superrigidity, and somehow have like a similar flavor of like to the work of Bader, Fisher, Miller, and Stover that probably some of you know. Okay, so let me tell you another result and maybe more kind of interesting questions which are related to to these questions, but are more like hyperbolic geometry, kind of. Okay. But are there any other questions?
I have one.
Yes.
Is your result is effective in the sense that you have bounds for the trace fields? For the extension of fields?
Effective. I mean, but like you have to give me gamma in some way, right? I mean, but if you give me gamma, I would already know it's like in some algebraic number field like of a given degree. But yeah, but I don't know. Yeah, so it would like in the algebraic field generated by the traces, but I'm not sure if you can go lower than that or something like. I don't know. Yeah, yeah. Okay. Yes. So. Yeah. Yeah, so let me tell you about other question of Alan Reed, which is related to this question, but okay, it doesn't seem too related, but it's very related. So the question is whether, so there is this question. Alan Reed says that, so suppose you have gamma, like in PSL to C, or isometries of H3, a lattice. And the question is, and let's look at the subgroup gamma 0. So this, because it's a lattice, is locally rigid, and locally rigid implies that the entries, or that you can conjugate it in such a way that it lies in PSL2 of some number field here, so some finite extension of Q. And then, so assuming this, well, you can look at the intersection of gamma with like matrices with integral coefficients. Okay, so this is a subgroup, and the question is, so what is this? How small can be this subgroup? So he asks whether can gamma 0 be equal to the trivial group. Okay, so it can all the, oh wait, maybe, I'm not sure if I'm stating, yeah, let's state it like this, okay? I hope this is equivalent to your formulation, Alan, okay, but yeah, so the question is whether, you know, the only, can you really find a hyperbolic 3 manifold whose all like matrices really have to have like rational non-integral coordinates, okay? Yeah, and and okay, and I think this is also not known. So there is like this notion of the critical exponent of a group of PSL2R or PSL2C that it just measures like in hyperbolic space how many like elements you have in a ball of radius n. If this is of the order of e to the delta n, this delta is the critical exponent. Or you can ask whether can delta, the critical exponent, be arbitrarily small. Yeah. And yeah, and I mentioned here that I think it's okay. Like it's possible. I believe that from like the available technology, like it's in the things that are in the proof or that I'll talk about, or like things related to it. I think one can possibly prove that this it has to be less than 2. Okay. Yeah. So I'll. Yeah. So okay. So let me tell you like a second theorem. Yeah. And the theorem is just like, okay, like, I don't think it's very useful, okay, but whatever. But it says that, suppose, so I have now gamma, like a lattice in isometries of Hn. And you would like to know when this group has algebraic entries, okay? Or, and it says the following, that is, and suppose gamma 0 is some subgroup of gamma, and this gamma 0, you know, has algebraic entries, or suppose one such that gamma 0 has algebraic or integral traces. And you would like to conclude that gamma itself has integral traces just from this smaller subgroup. But so it requires this condition, that is gamma 0 acts ergodically on the boundary of Hn, but also not only gamma 0, but all finite index subgroups act ergodically on the boundary. Okay? And then the conclusion is that gamma itself has integral traces. Yeah. So, yeah, I couldn't. So far, like we haven't been able to like remove this assumption here, that because like actually there are subgroups of like PSL2R which act ergodically in the circle, but have finite index subgroups that do not act ergodically in the circle, which is kind of amazing. Okay, and so we really need also like well, I'm not sure if we really need it, but right now we cannot remove this assumption. Okay, so for example, yeah, if you have a hyperbolic trimanifold, and the fibers over the circle has a geometrically infinite surface subgroup. If you know like all the entries are integral or all the traces of these are integral, then this group have integral traces. Okay, even though in that case, it's one can prove it in a different way, in an easier way. Okay. Are there any questions? Okay, so yeah, so I'll tell you like what is like in the proofs of these theorems 1 and 2 it follow from kind of these maybe abstract like result, which it's about actions of groups in discrete in Lie groups on buildings. Okay, so let me put like this kind of abstract theorem, and then I'll tell you something about the proof of it. Okay, so the theorem, let's call it theorem 3, which is kind of nasty. Okay, it says the following. It says, suppose I have a gamma G, a discrete subgroup, and suppose I have a discrete gamma 0 containing gamma, such that this gamma 0 like has like this assumption that gamma 0 acts ergodically in the boundary. So this is the boundary. This is the Forstenberg boundary. This P for SL and R. This is like the upper triangular matrices act ergodically, and also finite index subgroups act ergodically. And the second assumption is, okay, it is part of that we have like gamma acting on some building. Okay, let's say it's a tree. So this is a locally finite acts in X. This is a locally finite Euclidean building. Euclidean building. And suppose gamma 0 has a fixed point. Has a fixed point in X. And then the conclusion that I would like to get is that gamma has itself a fixed point in this building. But, okay, this is not exactly what it's saying. It's like saying that gamma preserves a probability measure on the boundary of X. But okay, you should think it as gamma like fixes a point in the interior of X, okay, or maybe a point in the boundary of X. Yeah. And then, so let me, are there any questions about this statement? Yeah, 5 minutes passed and you didn't correct me, I think, okay. So that's good, that's good. Yes. Yeah.
Gamma naught, if gamma naught is not the lattice, then the
Okay. If yeah, this is wrong. This is totally wrong. Okay. Yeah, I mean, this is less than 2 unless gamma has integral trace. It has integral unless gamma 0 is a lattice. Yes. Okay. Yeah, and yes.
To know if gamma is so condition number 2, where gamma not exergorically,
Uh-huh.
how is it connected with gamma? Should gamma 0 be Zariski dense? So
If it acts ergodically, well, okay, that doesn't. Yeah, that's probably follows from Zariski density. What?
so if it's not Zariski dense, then the limit set is much smaller than the boundary.
Yeah, but if then it would not act ergodically. I mean,
It would not
it would not
occur.
act ergodically. Yeah, but yeah, you always like assume Zariski density. If better to keep that in mind. Okay. Yeah. Any other mistake, Sami? No. Yeah. No. Okay. Yes. So. Okay. So I'll say why like theorem 3 implies like theorem 1, and then I kind of give an idea of the proof of like theorem 3. And so let's see, like, okay. So yeah, so I'll just so let's do theorem 3 implies theorem 1. Let's prove just this case, okay? And just to simplify things, let's assume we're in we're in the setting of SL2R times SL2R as in the beginning, okay? So let's suppose gamma 0 was SL2Z, and so gamma is containing SL2R times SL2R. And yeah, so why? So the idea is kind of like, okay. So first, okay, there's like a crucial observation. It's a crucial observation that is why, like, kind of, it's part of the reason that we have like this hypothesis of gamma containing this like diagonal subgroup, is that gamma acts ergodically on the boundary of this G, okay? Ergodically on the, if we call this G, on G mod P. Okay, in this case, G mod P is S1 times S1, okay? And the reason why gamma acts ergodically is because the lattice itself, this SL2Z acts ergodically on S1 times S1, acts ergodically. And the reason of this is equivalent to the ergodicity of the geodesic flow in the hyperbolic surface. Okay, this is equivalent to ergodicity of geodesic flow in H2 mod gamma 0. Okay, and yeah, so let me say that, okay, so that's like kind of like the why we cannot kind of have like a less like restricting assumption for our theorem. And yeah, and actually there's a conjecture of Margulis that, or like Sean Yao also attributed to it, that if you have a locally symmetric space in higher rank, let's say irreducible, and you have a discrete subgroup which act ergodically in the boundary, or this is equivalent to like the locally symmetric space, not like all the bounded harmonic functions being constant, all bounded harmonics being constant, then the group is itself a lattice. Okay? So like the Margulis conjecture said that ergodicity of the action in the boundary in G mod P is equivalent to being a lattice. Yeah, and actually he proved that if you act ergodically in G mod P times G mod P, then you're itself a lattice. So yes, so we have like this assumption that we need, and now so we just have to construct somehow, like if we can construct an action of this group in such a way that this one like fixes a point in a building, but the whole thing does not fix a probability measure, then we win. Okay? So we satisfy like these conditions. Like also finite index subgroups are also lattices ergodically. So we construct maybe I'll do it somewhere else because okay. So we just construct some actions. So I can make gamma. So assume, it's by contradiction, assume gamma was isomorphic to like gamma 0 free product with Z. And then let's take a tree. So for example, you can take the Bruhatitz tree of SL2C, take a tree where gamma 0 acts with a global fixed point. So yeah, so because gamma 0 is almost free, right? Like to finite index, yeah, you can make it act in a tree like in such a way that acts non-trivially in this tree and have a global fixed point. So this would be, but and then you make this one act in such a way, and a gamma action, like gamma action on T that does not preserve a probability measure, or so that, let's say, so that Z, this Z copy, Z acts loxodromically. I mean, constructing action of free products is very easy, right? You say how this acts, and then, okay, like in the boundary, if this acts loxodromically, like the only probability measures that can it possibly preserve are like the endpoints of the like axis of this translation. So, but if you choose gamma 0 acting non-trivially, if you choose gamma 0 acting trivially, well, you get nothing, but you just have to make sure that gamma 0 does not act trivially in this tree, but has a global fixed point. Then gamma does not preserve a probability measure. On delta x. on delta t. Okay, contradicting kind of like what this like thing is saying. Okay? Yeah.
Or maybe you mentioned this, but if you get an axon of every finite tree, you take a quotient of gamma naught or something. It's not that
Well, is the buzzer is like if you look SL2C acting in SL2ZP, there's the tree of SL2QP. That tree, I call this buzzer tree. That's not the buzzer tree? This is the SER tree?
But you're taking a tree associated to the splitting.
To the what?
To the splitting.
No. Yeah. Maybe I make it confusing that way. Yeah. Just any action. It's a. Yeah. I guess like yeah. Suppose this was a free group instead of SL2C, and then just make it act so that it doesn't fix like the endpoints of this geodesic. Then we're good. Yeah. Okay. And yeah. So, are there any other questions? Okay. So I'm gonna give like kind of a sketch of like the proof of this theorem, and we'll finish with that. Oh yeah. Maybe if I don't manage, I would like to mention some kind of like problems. So like open problem, or like things that I think like a question that is kind of approachable, and but we haven't been able to figure out. Like for example, like suppose gamma is a subgroup of SL2R times SL2R, but doesn't contain a diagonal like subgroup, but like an Anosov subgroup. Okay, so you have like two representations of like in SL2R, and you make like this joining that gives you like a surface in SL2R times SL2R, and then like to kind of apply to get like the same results. The only thing that we need to prove is that like this, if you have two representations, or like two Fuchsian groups, and you put them diagonally in SL2R times SL2R, whether these act ergodically in S1 times S1. Okay? In this case, it worked because, I mean, we have the same action here and the same action of the surface group here. But let's say you change the other action. Does this act ergodically with respect to the Lebesgue measure? Yeah. I didn't. I made a mistake of not defining ergodicity as well, but it means like any, Lebesgue set that is gamma invariant is full measure or zero measure. Okay, even though like the actions on this thing is not volume preserving, it's like loxodromic kind of action. Okay. So let's like, well, as I was saying, like the proof like lies in the ideas of Margulis in superrigidity and the ideas of Venkataramana Chatterjee, and so the sketch of theorem 3. So the first thing is the most difficult one, kind of coming up, is like that is it's related to like kind of the proof of Monster rigidity. When you look Monster rigidity, there's like a map between gamma invariant map between the boundaries, gamma equivariant map between the boundaries. So the like here like kind of the crucial thing is there exists some map. Phi map from G mod P into like the, I mean, you would like, this is the boundary of G. You would like to say into the boundary of X, but not really the boundary of X. You have the probability measure delta X. This is a measurable map. Okay, so it might be kind of crazy. and is gamma equivariant. So phi of gamma x, it's gamma acts in the boundary, but because acts in the boundary, it also acts in probability measures. So gamma of phi of x for every x, G mod p. Okay. And so like the existence, okay, I don't want to say anything right now about the existence of this map. I'll just say it exists. This is non-trivial. But it follows from work of Zimmer, and I can explain in private if you want later. Okay. And and now, so what we will do, so for simplicity, let's assume that the image, that we actually get a map to the boundary and not the two probability measures, okay? So assume we just have some map, measurable map into delta x measurable. And then and what we will prove is that this map is a constant map, okay? So it's a constant map and it's gamma equivariant. So what we will prove is that there's a point in the boundary that is invariant by gamma. So you have a probability measure that is invariant of gamma. I mean, you have a fixed point in x and you have a gamma invariant point in delta x. So it's like, then you're pretty good, okay? So that's what we will prove. And then, so okay, I'm gonna take some finite index subgroups. So we have gamma acting on the tree or like the building. And I want to call, and gamma 0 was stabilizing like this point. And I'm gonna call gamma n the stabilizer of the n ball of the tree. Stabilizer of like the ball of radius n of the tree. Okay? So it's fixing, gamma n is fixing this, but might be doing little things here. But the thing is like, here it's in the boundary, because it's fixing this, it's acting almost trivially. But this gamma n is acting ergodically here. Okay? And the idea is that, okay, like in the limit, like gamma n acts just trivially in the boundary, and this, but it still acts ergodically. So this map has to be, the only way that it can exist is that it's constant. Okay, so gamma n, so this is like a finite index subgroup. It's finite index subgroup of gamma 0. They are contained in, it's a chain. And okay. And we're like very close to finishing is, and if you, so I have this tree, and I'm gonna let, how do I call this? So I'm gonna let U be an open set in delta x that is gamma n invariant. So, okay, I have my tree, and I take here in the boundary this gamma n invariant set U. Okay? And I look at the preimage of this under my map. So now this one is gamma n invariant, right? And it's a set of the boundary that is gamma n invariant. And then, okay, so either has full measure or zero measure. Okay, then the Lebesgue measure of, yeah, I have to stop like now, okay, then, well, let me finish because we're very close. So this either 0 or 1, okay, and so this means like one of these like open sets have to have measure 1, okay, and I'm gonna call this, so let U1 so that has measure 1, so that Lebesgue of phi minus 1n is equal to 1. And then, okay, if I take the intersection of the UNs, this is just a point. It has to be a point. And all of these were, and the image of phi has to lie here, right? And that's it, okay? And I think I can stop here. Okay.